sklearnensembleStackingRegressor. Description: the stacking regressor in scikit-learn is an ensemble learning method that combines multiple base regression models to create a more powerful and robust model. It works by training a meta-regressor on the predictions of the base models. The meta-regressor learns how to best combine the predictions of the base models to improve overall prediction accuracy. Inputs: estimators a list of base regression models to be combined. Each element in the list should be a scikit-learn estimator object, e.g. linear regression, random forest regressor, gradient boosting regressor. Final estimator a meta-regressor that learns to combine the predictions of the base models. This can be any scikit-learn regression estimator. Outputs: predictions, the predicted values for the target variable, based on the combined predictions of the base models. Steps: Stage 1, the base models are trained on the input data. Stage 2, the predictions of the base models are used as input to train the meta-regressor. Stage 3, the trained meta-regressor is used to make predictions on new data. Combining the predictions of the base models. Metrics: mean squared error MSE measures the average squared difference between the predicted and actual values. Root mean squared error RMSE the square root of the MSE, providing a measure of the prediction error in the same units as the target variable. R squared a measure of the model's goodness of fit, indicating the proportion of variance in the target variable that is explained by the model. Mean absolute error may measures the average absolute difference between the predicted and actual values. Visualization plots: residual plots visualize the difference between the predicted and actual values to identify patterns or outliers. Feature importance plots visualize the importance of each feature in the model's predictions. Learning curves plot the model's performance on training and validation data to assess model complexity and identify overfitting or underfitting. Fine-tune parameters: estimators experiment with different combinations of base models to find the optimal combination for your specific problem. Final estimator choose a meta-regressor that is suitable for the type of data and task. CV the number of folds to use in cross-validation when training the base models and meta-regressor. N jobs the number of CPU cores to use for parallel processing. Uncertainty methods: confidence intervals provide a range of values within which the true prediction is likely to fall. Prediction intervals provide a range of values within which the true prediction is likely to fall, taking into account the uncertainty in the model's parameters. Challenges and fixes. Challenge 1: overfitting when the model is too complex and learns the training data too well. It may not generalize well to new data. Sample use case that resulted in challenge 1: training a stacking regressor with a large number of base models on a small dataset, leading to a high variance model. Fixes to challenge 1: use regularization techniques, e.g. L1 or L2 regularization to reduce the complexity of the models. Use cross-validation to select the optimal model complexity and avoid overfitting. Employ early stopping to prevent the model from training for too long and overfitting the data. Challenge 2: high computational cost. Stacking regressor can be computationally expensive, especially when using many base models or a large dataset. Sample use case that resulted in challenge 2: training a stacking regressor with multiple complex base models on a large dataset, leading to long training times. Fixes to challenge 2: use less complex base models to reduce the computational cost. Use parallel processing to speed up training. Consider using a subset of the data for training if computational resources are limited. Challenge 3: data leakage. If the meta-regressor has access to information that was used to train the base models, it can lead to data leakage and over-optimistic performance estimates. Sample use case that resulted in Challenge 3: using the same data to train both the base models and the meta-regressor, resulting in the meta-regressor being able to cheat and learn patterns from the training data. Fixes to Challenge 3: use cross-validation techniques that ensure that the meta-regressor is trained on data that is not used to train the base models. Use a holdout set of data to evaluate the model's performance without data leakage.